All right, guys. I hope that this is audible to everyone. Sorry. Okay. So we were discussing about rolling, and over here there is this point over here. Let's consider point G and the point P. Right. So when we say rolling, then the relative velocity of the point P with respect to this point G is nothing but equal to zero itself. Only then can we say that rolling motion exists. We also say that there is a condition called as no slip condition. And not only is this one true, uh, if you were to consider over here, let us say that this is a plank. Uh, on the plank, there is the sphere over here. Right? Suppose the plank were to move with a velocity of 10 meters per second. Right? That means this point over here would be moving with what velocity? 10 meters per second. If you do not want this particular cylindrical or spherical object to slip, this point must have the same velocity as the point called the G point, which means this one must also have 10 meters per second. Why? If they had, let's say, that one had 11 or that one had 9, in that case, either it will move faster compared to the plank where it is in contact, or it will move slower, which means it will slip along the common tangent. Fine. Not only is this true, you could have another case where you have over here the circular, not elliptical, circular bounded object. Oh my god. And this one over here is rolling in between two planks in this way, right? This way. And over here, this the plank at the top may be moving with a 20 meters per second, and this one over here it may be moving with a velocity of, let's say, 10 meters per second. And even in this case, uh, this particular object, if it is in which kind of motion, if it is in rolling motion, then at this particular point over here, the velocity of this P point must match the velocity of the plank, which means that if plank is moving with 10, point P must also have 10 meters per second and in the same direction. In the same way, at the top point also, the two velocities must match. So it would be how much in this case? 20 meters per second. And this particular direction is also known as the common tangent direction at the top. This one over here is the common tangent. It means it's tangential to both the surfaces which are in contact, the sphere as well as the plank. Right? Okay, not only is this one true, but what if you had acceleration? Right? Well, even then we can have rolling motion. For example, this plank over here is moving with an acceleration of 4 meter per second squared in this direction. Right? This point over here along the common tangent, if it were to have the same acceleration as that point of the plank, then we say that this motion is also what kind of motion? It is rolling. And since there is acceleration over here of that acceleration of the center of the mass you would have over here, we'll come to that. But in this case, we would say that it is an accelerated rolling motion. Okay? Accelerated rolling. Okay. So now let's let's come into the details of why this is true, right? Why and how do we find out those velocities of the object? Fine. So first of all, we'll write that the velocity of any point can be written as the velocity of the point with respect to some other point plus the velocity of that some other point. Right? Why this is true? Since The relative velocity by definition is given as the difference between the two velocities. So if you were to shift the minus Vc to the left hand side, the Vp's will be given by this one over here. Fine. So let's go to the circular boundaried object over here. Fine. Fine. And over here, this is the point called the P point. And this entire rigid body is having an angular velocity of omega, let's say, about the center of the mass, let's say. Okay. Which means what? That this particular point P would be having a velocity towards the left. Okay. And how much will that be equal to? It would be, wouldn't it be r omega? Yes. Now imagine that this is nothing but your fan over here, and that's one end. The P point is the edge of that fan. And what if I were to move the entire room in which you are sitting? Can we say that the center of the fan would also be moving this way? Right? With what velocity? With the velocity of, let's say, v it is. Right? So will we? So can we say that this point over here, the edge of the fan, would still be rotating around the center with the same speed? Is the speed of that fan with respect to the axis, is that going to change just because the entire room is moving? No, that will still be the same. Right? So therefore, even now, we will write that the velocity of the point P with respect to the center is nothing but r omega. If you take the rightward direction as positive x-axis, then it would be minus I cap. And what would therefore be the velocity of the point P? The velocity of P with respect to C plus the velocity of the C point, which means it is r omega in minus I cap plus what is the velocity of the C point? Some V value it is, right? V in I cap. So now let's put the ground over here. Right? Since we are studying the rolling on the ground first. Right? So for no slip, the velocity of the P point and the velocity of this point over here, they must match. But the ground has no velocity. That's why it's called as the ground, right? Otherwise, it would be called as maybe platform, right? That would be moving ground. That would be an earthquake. No, right now let's consider that there is just the stationary ground over here. And therefore the Vp must be equal to how much? For rolling motion, and is also known as the rolling constraint, Vp must be equal to Vg, which is nothing but equal to 0. And therefore it is r omega in minus I cap plus velocity of the center in I cap, which means what? V is nothing but equal to r omega. This is nothing but your which constraint? Rolling constraint. Okay. All right. So what if it was rolling on a platform? Let's do that. So over here, let's consider another case. I hope you have taken this down. If you have over here circular bounded object, and this is a plank over here. Okay. And this plank over here has 10 meters per second. Okay. Let's say that this one over here has 5 meters per second. This one. Okay. The radius over here is given to you as equal to, let's say, 2 meters. And you are asked to find out what is the value of the angular velocity and in which direction is it spinning? Is it spinning to the right side or to the left side, clockwise or anti-clockwise? So therefore, and it is given to you that it is rolling on whom? On the plank itself, rolling on plank. So therefore, if it is rolling on the plank, we'll go to these 2 points over here, the point P and the point called G. The point P should have velocity same as the point G over here. Okay. For this, we'll have to assume any one direction as omega. Let's assume that omega is this way. After solving, if you get omega as positive, it means whatever you assume was the correct sense of omega. That means it is clockwise. Otherwise, we just have to reverse it, keep the magnitude. Fine. So therefore, let's use the ruling constraint. Velocity of P is the velocity of G. The velocity of G is 10 I cap. Velocity of P is with respect to the center plus the velocity of the center. With respect to the center, it has r omega this way in minus I cap, plus the center has a velocity of 5 to the right side in I cap. Substituting, what do you get? R is 2, omega we do not know, minus I cap, plus VC is how much? 5 in I cap. This is 10 I cap. On comparing the coefficients, shifting the terms, can write this as 5 I cap, 10 I minus 5 I, and this is 2 omega in minus I cap. Or you can write minus 2 omega is equal to 5, which means that omega is minus 5 by 2, which is 2.5 radians per second. It means that the sense of rotation of this object is not clockwise. It's actually rotating this way. Right? And the magnitude of omega is 2.5 radians per second. Fine. So you can imagine how it is, right? It's like trying to pull a carpet underneath the object with a high velocity over here, and turns out that it will spin this way instead of spinning the other way. Whereas it will still move, the center moves to the right side over here. Fine. All right, so let's take another question. Okay. The same process we are going to repeat, but now let's make it roll in between two planks over here. Right? One plank, and this is the other plank. Right? This is moving with 10, and let this one move with, say, 15. Right? And this object is given to us to be in which kind of motion? Given to us to be in rolling motion. Fine. So therefore, if this is in rolling motion, then let's try to find out the value of the velocity of the center as well as the angular velocity of this object. And we are given the value of the radius. The radius is, let's say, 2 meters. Okay. So therefore, again, let's apply the rolling constraint at the top as well as at the bottom. Right? So over here, we can write that this is the P point, and let's call this as the T point. Over here, this is the P dash, and the G point. Right? So therefore, the velocity of T must be equal to the velocity of P. Velocity of T is which way? We'll have to make some assumptions about this omega, right? Let the omega be clockwise. Let the velocity of the center be to the right side. And we are taking this direction to be positive. Positive x-axis. Fine. So therefore, Vt is nothing but how much? Is it minus 15 I cap? Definitely. And velocity of P, can we say that with respect to the center, the P point has r omega to the right side? So this becomes r omega in I cap plus velocity of the center is also to the right side. And let's substitute the value of r over here. How much is that? It's 2, right? Okay. We can't solve for omega or v. We need one more equation. So let's go to the bottom. And we will write that velocity of g must be equal to the velocity of P dash. For the G, the bottom point, the Planck's velocity is 10 in I cap. And at the bottom, the R omega is about the center. It's to the left side over here. Fine. So therefore, and the V is to the right side. Let's add these two vectors with respect to the center and the velocity of the center. And let's substitute the value of R just to equation number 2. This one is. So let's add these two equations to remove the omega part. Minus 15 plus 10 is how much? Minus 5. And Vi cap plus Vi cap is 2Vi cap. Therefore, we can write 2V as minus 5, which means that V is minus 2.5 meters per second. That means the direction of V that we took is incorrect. It should be moving in the leftward direction. Fine. Fine. And now for the omega, we'll take this value of V, put it in any one equation. Let's put it in this one. So what do we get? Therefore, tan I cap is minus 2 omega plus Vi cap, which is minus 2.5 I cap. And shifting the terms, we get 2 omega as equal to minus 12.5, which means that omega is minus. Comparing the coefficients of I, this is 6.25. Fine. Units are radians per second. And therefore, again, since you're getting omega as negative, it means it's spinning in the opposite sense to whatever you assumed. So, to whatever we assumed, sorry. Therefore, over here, the actual omega would be this way, the actual velocity of the center would be this way. 2.5 meters per second to the left, 6.25 radians per second anti-clockwise. Fine. All right, so this one is clear. Okay, let's end the class with this one. We'll continue with rolling in the next class. Fine.